The John Rylands Library has always recognised the need to photograph its collections. This is an extract from a minutes book on the establishment of a photographic studio. The value of the treasures of the library is greatly enhanced for purposes of research, since they are made more readily available to scholars at a distance, and there can be little doubt that this new department is fraught with possibilities of worldwide benefit. This was over 100 years ago. That statement hasn't really changed, but the methods and techniques used by the imaging team have. At present, we use a medium format digital camera system by phase 1. The 150 megapixel digital back provides the greatest photographic detail and information possible. Let's take a look at existing historic data and an example of the importance of accurate data for online digital research. On the left is an older scan transparency photo that was available online for many years. Compare this with a more recent digital born image following a research project within the imaging team. The difference is remarkable. It's difficult to think that they're the same item. Photographer Gwen Riley-Jones, now imaging manager, carried out research into the best ways to image gold illumination. It was found that the standard flat copy reproduction techniques used by many institutions may not be showing their collections in the best light. We invited Cheryl Porter, a leading pigment specialist, to work with us on the project. We used original methods of pigment application and studied different types of gold and how they react to light. By understanding how they were applied, informed how we could better image our collection items. Here's an example of standard flat copy studio lighting. It's not bad. Colours are accurate with a small amount of gold highlight detail, but there's still room for improvement. With our adapted workflow, the difference in results is significant. Maintaining the correct colour accuracy without blowing out the highlights whilst enhancing the gold areas. This new method picks up on the gold wonderfully. Also notice now the gold flecking that covers the page. This technique could then be used for other materials that can prove problematic for imaging. This is Trier Binding 17, a highly decorated and ornate ivory carved inlay with semi-precious stones. The usual standard lighting looks very flat. The gold is dull. You can't really see the detail of the stones. By using our adapted technique, we now get a much more realistic impression of the gold, and the stones are much more visible. The inlay becomes clear, and you can appreciate the depth of the carving. We discovered that these different lighting techniques could be used for further applications. Here we see the damaged pigment in the face much more clearly than we had seen using standard lighting. These 3 different lighting techniques each display different characteristics of the surface material of the manuscript. With the naked eye, the pigment damage was hardly noticeable. This sampled area is about the size of your little fingernail. A combination of the high-resolution camera and adapted lighting technique shows up damage incredibly well, to the point of being able to see the depth of the layers of pigment. It's not just our established workflow that changes. Here's an example of technology becoming increasingly automated. This is an example of focus stacking, a technique that would have been quite time-consuming in the past. Now, it's an automated feature within our digital camera equipment. It's especially useful for macro photography, where there may be limited depth of field. That's the area of interest that's in acceptable focus. Focus stacking takes a series of images whilst changing the point of focus. The images are then combined using software to produce one image with precise and defined points of focus from front to back. Here's an example. What may have taken for many hours now takes a matter of minutes. Here's a more involved imaging technique called reflectance transformation imaging, or RTI, also known as polynomial texture mapping. An item directly below the camera is photographed several times as a light source moves around it at varying heights. There are commercially available domes with built-in LED lights, but this technique can be achieved rather simply with just a handheld flash. We use a handheld flash and a length of string as a guide for this very purpose, usually making 3 circuits at 3 differing heights, resulting in 72 images. The images can be imported into the RTI Builder and Viewer software, both of which are free to download, and I'll provide links at the end of the presentation. The RTI Viewer software lets us investigate the surface of the item, in this case papyrus, in the form of the St. John fragment. In the viewer, you can manipulate the light source to simulate a light moving around the item. This lets you study the surface texture in great detail, in full color or in one of the other rendering modes such as specular enhancement. This is a straightforward if underutilized imaging tool. Another imaging technique now being used at the John Rylands Library is photogrammetry, also known as structure from motion. Here, a series of images are taken of the item from a number of differing angles. The photogrammetry software then measures and combines the images into a 3D object. This is an example of a bone effigy of John Wesley, made from a horse vertebra. We're able to interact with it from any angle. It can be annotated, animated, and overlaid with additional visual information. It can also be used in virtual and augmented reality and 3D printed. These 3D objects are currently viewed online via the platform sketchfab.com. I'd like to include this example of a simulated 3D object. I say simulated as it's created from just one digital image. The daguerreotype is notoriously difficult to photograph. It has a mirror-like surface that is especially difficult to display in a digital format. Using the tools available in Sketchfab, I was able to simulate the material surface of the daguerreotype, something that has been impossible to do in the past. I think this is a good example of reusing old data with a new technique. This enhances and furthers the study and research of our collection items online. At the John Rylands Library, we've been developing our multispectral imaging workflow since 2012. We've been fortunate to work very closely with some of the developers and other institutions such as the Library of Congress in the United States. In its most basic form, multispectral imaging allows us to see things we wouldn't normally see with the naked eye. We do this with a range of narrowband LED wavelength-specific lights with an orthochromatic digital camera. We capture images from UV at 365 nanometers through to near-infrared at 940 nanometers. We can then process that data in a number of ways depending on the research question. The most common examples of MSI use are probably the imaging of palimpsests. This is where the writing material, such as parchment, has been cleaned of its original text and reused. Here's an early collaboration effort between the imaging team and students from the School of Physics and Astronomy. This is Greek Papyri 465. The first image is just standard lighting, as you would see with the naked eye. The second image is UV 370 nanometers. This makes the overtext and undertext a little more visible. The third image is infrared, 940 nanometers. The undertext has become, let's say, transparent, and the overtext much more visible. The fourth image on the right is the processed imaging. The students then used math encoding to combine the two to show the difference in pixel values, thus making the undertext much more visible. This was one of our very first experiments. Once one is aware that different materials react to life in different ways, you can begin to apply that to specific materials. Here's a crop of an engraving by Marcantonio Raimondi. The researcher was interested in seeing the carbon underdrawing, which was below the iron gall ink. On the left is the engraving as you would see it with the naked eye. On the right is an image taken with near infrared. Carbon and iron gall both react differently to infrared. And here you can see the over ink has disappeared, for want of a better word, leaving the carbon underdrawing clearly visible. One can apply the same principle to the other end of the electromagnetic spectrum. This is from a project with the National Library of Scotland. Here, the iron gall ink, notorious in some cases for fading, has been enhanced by the use of UV light. In this example, it's also been inverted so it's white text on a black background. Some people find this easier to read. It's probably a good point to mention that we work very closely with the researchers to ensure we're providing data which is truly useful to them. A more recent example of MSI success can be seen in the Leverhulme-funded project of Professors Joan Taylor and Marcello Fidanzio and Dr. Dennis Mitzi. Their research has helped reveal that 4 Dead Sea Scroll fragments housed at the John Rylands Library, which were previously thought to be blank, do in fact contain text. The discovery means that the University of Manchester is the only institution in the UK to possess authenticated textual fragments of the Dead Sea Scrolls. Here, a very small fragment of Dead Sea Scroll material can now clearly be seen to show in text. These and many other fragments have sat in the original boxes from when they were first given to lecturer Ronald Reed in the 1950s, who was an expert in leather fragments. I'm sure we'll be revisiting this material sometime soon. Multispectral imaging is not just for revealing the invisible. It can also be used to help identify pigments. This is a non-invasive method which can be used as a precursor to other investigative techniques such as XRF, FORS and Raman spectroscopy. With our MSI equipment, we can sample and analyze the reflectance of material and plot the results on a reflectance curve chart. Here we have a number of well-known blue pigments. These have been laid down by our collection care team. It's been imaged using MSI and each sample is plotted in the chart. This gives us a library of known pigment samples. These were then used as a comparison against MSI samples from Latin manuscript 30. John Rylands Research Institute Exchange Fellow Sarah Bromberg was interested in seeing if the blue pigment that was used extensively through the manuscript was in fact lapis lazuli. Here, one sample area of blue pigment from the manuscript is plotted against the nearest of our known blue samples. It can be clearly seen that the spectral curve is almost identical to that of lapis lazuli. You can see some difference in this area here of the chart. One can conclude that there is very good probability that the pigment used is lapis lazuli. The data collected for that particular project was then used by another researcher and academic, Carol Twining, senior scientist in the Faculty of Biology, Medicine and Health. She and her PhD student were looking for data to use in their investigations, which would normally involve brain matter, and they were excited to be able to use MSI data from another source, the John Rylands Library. I'd only commented to a colleague days before that it'd be great if someone could write some script that at the click of a button one could identify specific pigments used in a manuscript page. Within days, here's what they came back with, along with a request for a lot more data, which we were very glad to provide. An excellent example of data reuse by another researcher and academic and a PhD student. We look forward to seeing what they come up with. Speaking of data, these imaging techniques create a huge amount. This needs to be stored, catalogued, and associated metadata created. In January 2020, the University of Manchester launched the Manchester Digital Collections, a metadata-rich, high-resolution image depository for research collections. In the coming months, this will be populated with research-specific special collections material. We're very keen to hear from researchers and how imaging can help them advance and support their research. We'd also love to hear about projects where imaging has been key to their findings. If you have any questions at all, then please contact us at the email address on the next slide. Thank you.